Welcome to the Parker office hours. It is August 13th, 2024. We are alive and happy. We have a lot of new releases and we have a big new Parker agent release, and we're easy query mode. I'm going to share a local instance of Parker that is running on my machine. So the data might sometimes look a bit funky because it's a desktop machine, not actually a server. So just to keep that in mind. But yeah, first things first. Yomi, you want to take it away?
Yes. So like Matthias said, we have shipped a lot of stuff over the past few weeks, months even. And one of the first things is the simple query mode, which is now on 0.22. So you can check it out. But the idea here is that we previously had only the freeform method. So if you go to the advanced mode, we had the freeform method where you could type in stuff, you can do some regex, and just basically use your keyboard to type in stuff and do some querying. But then we also had feedback that some people might prefer a mode where it was easier to easily select stuff around instead of just typing. So basically that's what this is about. You get to type in your label names, type in your label values. You can add as much as you want, and that's the idea behind.
In Parker is the relative comparisons, and those are enabled by default if you use on.
We have implemented the most up-to-date version of the experimental protocol that's currently specified. Now there's a huge caveat.
Is calling that specific function. So here we see the
kind of select any profile here. It doesn't really matter. The point is we now allow kind of inverting the stack. This is a feature that has been requested a couple of times. So this can again be interesting if you want to see everything that ends up being a leaf, like malloc, for example.
Yeah, so
and actually this is a great so if you now hit invert call stack, we can turn it around and we can find all the things that do some sort of allocations, right? And we can find out all the code paths that have caused these allocations. So again, kind of an interesting way to now kind of visualize this. Now, this only works if the thing that you're looking for is the leaf, right? And especially with memory allocations, this is often the case. So that's why this works out quite well here. So yeah,
that's we can see the operator new again that we saw in the callee or caller table. So it's pretty exciting.
That's the last visual feature we have to talk about. The next one is kind of this has been coming for a very long time. So
let's see what he has on his bookshelf. Prometheus up and running, site reliability, engineering systems performance, designing data-intensive applications, the workbook for SRE, 2 bugs I can't identify. This one, operating OpenShift, just Kubernetes, distribution from Red Hat. Some fiction books over here, looks like. These are good books. I own 1, 2, 3, 4 of them. I do not own Prometheus up and running. What does ICMP stand for? Hey, I got it right. First edition, published 2018. I remember that being a book that people had in the office they were reading. I'll add it to my list. Why not? Oh, it's a new edition. Cool. Yeah, I was gonna say. Wonder if there's a newer edition. So this is 2023. So we'll take that, jump over to our learn log, which we already have open here. And this is going to be under books. Okay. eBPF is not really security related. Why did I put it under there? I guess that book does have an emphasis on security, doesn't it? It could be between security and performance, since I already have some performance stuff. All right. Let's continue. Kill this. Go over here. Okay. We don't need this anymore. That was a little problem we did. What was this guy up here? Oh, that was our tracker there. Okay, let's continue reading. Among compilers, GCC is considered adequate but not exceptional in terms of its optimization capabilities. It performs basic optimizations, but it does not perform the radical transformations on programs that more aggressive compilers do. As a consequence, programs using GCC must put more effort into writing programs in a way that simplifies the compiler's task of generating efficient code, expressing program performance. We introduce the metric cycles per element of an array, abbreviated CPE, to express program performance in a way that can guide us to improving code. CPE measurement helps us understand loop performance of an iterative program that, at a detailed level, it is appropriate for programs that perform a repetitive computation, such as processing the pixels in an image or computing the elements in a matrix product. The sequencing of activities by processor is controlled by a clock providing a regular signal of some frequency, usually expressed in gigahertz, billions of cycles per second. For example, when product literature characterizes the system as a 4 gigahertz processor, it means that a processor clock runs at 4 times 10 to the 9 cycles per second. And that's an insane amount of cycles. The time required for each clock cycle is given by a reciprocal of the clock frequency. These typically expressed in nanoseconds. 1 nanosecond is 10 to the minus 9 seconds, or picoseconds. 1 picosecond is 10 to 12 seconds. For example, the period of a 4 gigahertz clock can be expressed as either a quarter of a nanosecond or 250 picoseconds. From a program's perspective, it is more instructive to express measurements in clock cycles rather than nanoseconds or picoseconds. That way, the measurement expresses how many instructions are being executed rather than how fast the clock runs. Many procedures contain a loop that iterates over a set of elements. For example, functions psum1 and psum2 in figure 5.1 both compute the prefix sum of a vector length n. For vector A, the prefix sum p is defined as p0 is equal to a0, pi is equal to pi minus 1 plus ai. So it's summing along as it computes the results. It just continues to sum. It says, okay, give me the previous value, add it to the current value, previous value, current value. Yeah. The function psum computes one element of the result vector per iteration. Function psum2 uses a technique known as loop unrolling to compute 2 elements per iteration. We explore the benefits of loop unrolling later in this chapter. See problems 5.11, 5.12, and 5.19 for more about analyzing and optimizing the prefix sum computation. The time required by such a procedure can be characterized as a constant plus a factor proportional to the number of elements processed. For example, figure 5.2 shows a plot of the number of clock cycles required by the 2 functions for a range of values of n. Okay, let's look at that. So we'll look at the prefix sum functions. These functions provide examples for how we express program performance. So we've got compute prefix sum vector A. So you got p sum 1, float a, float p, log n, so long n, n is the amount of elements in both arrays. We initialize the 0th element. We start from the first element, going from that to the length minus 1, and going I++. Pi is equal to pi minus 1 plus pi. That's exactly how I'd implement it. So they do some loop unrolling here, where they do the same initialization, but they go I is less than n minus 1 this time, so it's guaranteed to be at least 1 left. Oh no, we might be even, in which case there isn't 1 left, but we could be odd. Oh no, but we also did the first element, which would make it odd. Okay, so say I is equal to 1, now we're odd. Up to the length minus 1, not including the last element. And we're going by 2 elements, and we're just taking mid-val, where we say, hey, mid-val is going to be p sub I minus 1, the previous value, plus AI. And then we're also going to add that value to pi plus 1 plus ace I plus 1. Okay, so now we're handling 2 elements per iteration. And we get to the end, and for n, for an even n, finish the remaining elements. If I is less than n, which means I plus equals 2 actually had a remainder element. Okay, that makes sense. Then we handle the last element. These functions provide examples for how we express program performance. So psum1, which is how I would implement it, has linear growth. psum2 has linear growth, but the constant is better. Performs a prefix sum function. The slope of the lines indicates the number of clock cycles per element. Let's go back to here. Using a least squares fit, I have to ask AI, what is a least squares fit? The points don't lie perfectly on a line, since you choose m and b that minimize the sum of squared errors between the predicted values and actual values. I mean, it's a pretty tight fit there. Okay. Find that the run times in clock cycles for psum1 and psum2 can be approximated by the equation 368 plus 9 times n and 368 plus 6 times n, respectively. These equations indicate an overhead of 368 cycles due to the timing code and to initiate the procedure, set up the loop, and complete the procedure, plus a linear factor of 6 or 9 cycles per element. For large values of n, say greater than 200, the run times will be dominated by the linear factors. Ask AI here. So you have to put a memory barrier. Couldn't you just use a 64-bit integer instead of low and high? I guess this instruction requires two 32-bit operands. RDTSC. Okay. RDTSC. Same instruction. This one end is RDTSCP partial. I just had a moment of anxiety because I'm learning from AI here. And I'm like thinking, okay, well, at what point in my future career will I require this knowledge off the cuff? And I can't use AI to just generate it. And I mean, like, AI isn't right 100% of the time, but for stuff like this, I might just have it generate it, you know? But yeah, that caused some type of like anxiety. So I'm like, am I wasting my time learning this shit? Does it feel like I'm wasting my time? And then it comes back to like, okay, we only have so many hours on this planet. It's so scary thinking about death when you're trying to be productive. Like, what do I want to do with my life? That's what I wanted to talk about last night, but it kind of like ended up being just like a session where I planned out all my learning for the year. But I have this, sorry, I'm like completely sidetracked here at this point. But I have this like game plan for the year to learn all this stuff, and I'll feel fulfilled. I mean, I feel fulfilled just in what I've accomplished up to this point of the year, the first quarter. I read the Linux programming interface. I read KNRC. I did all the extra, or not all the extras, but a lot of the exercises in both. And I read like a good chunk of this computer systems of programmers perspective. And I feel fulfilled. Like, I'm learning a lot. And I'm going to continue to learn a lot. Like, this stuff ahead of me with parallel computing, that's stuff I've been wanting to like spend time learning for ages now. And I'm going to dedicate the time and I'm going to do it. Along with the BPF stuff, like, I'm going to spend a good amount of time this year just learning stuff that I really care about. Like the C++ concurrency in action book. I read a concurrency book, the Java one, but the C++ one I was meaning to read for a while. I just never got around to it. That's on the table. The operating system's 2 easy pieces, because I'm not doing the third. The systems performance book, which is like the book that like everyone has on their bookshelf. Like, I'm getting these big projects done, big learning projects done. And I'm going to feel fulfilled and accomplished. But I only have so much time on this planet. Like, is this actually what I want to do with my time? I feel pulled towards it. It's like, this is what I default to, is just learning stuff that interests me. That feeling of accomplishment, I feel pulled towards it. It's served me well in my career. I'm happy in the things that I've accomplished. But is this like the meaning of life? Like at the end of the year, will I be able to look back on all these accomplishments and all these things that I learned and feel like this was a solid use of my time? Or will I have felt like there's so much that I haven't learned because I've been so laser focused on these individual projects? Like, do I need to spend like a month casually reading the Linux binary analysis? I mean, I've learned a lot so far just reading the first couple chapters. But like, do I need to spend the rest of the April doing that? I don't know. I don't know, to be honest. And like building products and companies is like another thing that I feel drawn to. But will that lead to me being happy and fulfilled? What if I spent like my entire life just dedicated to learning? And then I get to the end of it and I die, and all of that learning is for naught. Like, you can learn all of these things and then you just die. It's like all this effort to build knowledge for knowledge's sake, and then you just fucking die. I guess the idea being is that you build knowledge to contribute to the body of knowledge. To educate others. To educate the next generation, because we're caught in this stupid loop of death. Think of how much more we could accomplish as a species if we could just have like a couple hundred years on this planet of healthy living. It's probably the biggest problem that we face as a species is like combating death. Combating death and disease from aging, age-related disease. It's just like this entropy that's eating away at your biology. You could do all these things to help stave it off, but ultimately, death is coming for us all. We're all gonna fucking die. The most horrible thing imaginable, death, is going to come to us all. Makes you really cherish the time that we have. We have so little fucking time on this planet. I like when I feel like I have accomplished huge thing in a small amount of time, it feels like everything is possible. It feels like even though I know my time is limited, it almost feels like I have infinite time. Like this beginning of this year, I read the Linux programming interface. I was reading 100 pages a day. And a lot of that didn't really, I mean, to be honest, when you're going that fast, like it's not really sticking at that point. Some of it was just material that was not super necessary for it to stick for me. Like all the fundamentals and interesting areas, like I spent my time going through and I read at a much slower pace. But when I was reading at 100 pages a day, I was like calculating how fast I could read stuff. And I was like, shit, I could get through so many books in such a small amount of time. But then reality hit, and I have like motivational fluctuations in the amount of motivation that I have, and the amount of time that I devote for things, and the amount of distraction that I allow into my life, and the amount of burnout that I can tolerate, and boredom. Those are all variables that fluctuate, and it kind of averages out to me getting like a solid 100 pages of technical material done a week, which is like such a slower rate, to be honest. But I use that rate as a guide for planning out this year. And now when I'm looking at it, I'm like, okay, this is a reasonable amount of stuff to have accomplished this year. But it still just shows to me how finite my life is and how little time I actually have. I wish I could just snap my fingers and have an infinite amount of time and like just spend it learning, nonstop learning. Well, I guess given that my time is limited, the best thing I do is optimize for the amount of learning per unit of time. It's an optimization problem. If I can learn at a faster rate, I can accomplish more in the year, and I will feel more fulfilled in how the year has progressed versus less fulfilled. Yeah. Sorry, this whole like anxiety rabbit hole I fell into. It's something that's been like brewing in my head for a while. And if I don't like talk through this stuff and like think through it, I'm going to avoid it. And when I avoid it, that leads to me avoiding life. And I'm done doing that. I spent so much the past couple years just avoiding the things that bring me joy for distraction, because I didn't want to deal with the idea that my life is finite, that my resources are finite, that my time is finite. And seemingly what I can accomplish is often much smaller than what my ambition would want. My appetite is always greater than my ability. My ambition is always greater than my ability. But those moments where I feel like my ability is greater than my appetite, that's the good stuff, man. That's when I feel alive. That's when I feel excited for the possibilities. Looking at this map I have in front of me, I'm not excited about it. Like, I would be excited about that if I could finish all of this by July. But it's just like unreasonable for me to push myself that much. But given all this stuff here, if I could cram that into a 3-month quarter, that's insane. That is absolutely insane amount of material. But I would feel incredibly accomplished. And maybe that's what I need to do. Maybe I just need to fucking laser focus, stop wasting time, stop spending time on things that are details, and spend more time on making progress on the, like, less depth, more breadth. I get caught up in these like pockets of depth that I get a lot of enjoyment out of, but they just consume a lot of fucking time. Whereas I think what would serve me well moving forward is more emphasis on breadth, less on depth. Depth where it's appropriate. Breadth. Because, like, I mean, you got so many different topics here. Like, you're not even touching on ML this year, or compilers, or your linear algebra work that you did 4 years ago. This is really, oh, that's, yeah, okay, cool. What happens when this is in light mode? Cypher 0 dev? Yeah. Thought incognito would do that. Huh, guess not. Maybe if I do like a different. Is there a light mode? Here, we'll just go over here and say, oh, maybe I can do like an archive. No. Yeah. That is. Or archive. But today. How about you put a fucking new line in there, bitch? Alright, it doesn't work. So annoying. Well, let me pull it up on my other computer over here that has light mode enabled. Cypher. I can't even do that on my computer. Alright, well, I guess we can disable light mode on the browser. We'll go here and say settings. And so annoying. Browsers managed by your Chrome flag for disabling dark mode. Disabled. I need to restart it now. GitHub.com. So annoying. There we go. So it doesn't show up very well in light mode. Because this is light mode here. Oh, interesting. Let's try getting that to work. I know this is a huge rabbit hole, but yeah, I don't want it to be ugly like this. So we'll call this images. So images, diagrams, MV 2026 star into images, CD into there. Then we'll say MV 2026 schedule 1. We'll make this be schedule 1 dash light. Oh, sorry, dark. Dark. Schedule 2 dark and objectives. Okay. So if we go now to Excalidraw and we do our open on images, this thing, and then we say theme is going to be light. This is much different. Much different than the stuff output by the dark mode. So we'll do this and say export image, no dark mode. Light mode. No background. No embed scene 2x SVG. So we'll say objectives light here. SVG. And then we'll delete this along with this. Then everything from here over, including this and this. And that will be export image, SVG, schedule 1 light. Oops. SVG. Then we undo all that. Then we delete everything from here on. Does that include July? Don't want to do that. Let's delete this travel here. Say export image, SVG, schedule 2 light. Alright, so now we have our light and dark. We can just reset canvas. And then here in README, instead of doing that format, we do this picture format. Source media dark will be images. This will be objectives. Sorry. And then this will be images. Sorry. 2026 objectives light.svg. And then we have to have our alt text. Alt is equal to okay. Let's run our grip now. Grip on README. See if that works. Does not look to work here. What if I do dark mode? So back over to here. Say hey, go to dark. Reload. Does not appear to work. Inspect. Did we get a picture? Well, it's because none of the images worked. Oh, because then they're images, right? Did I mess that up? No, that's right, images. Okay, so those images worked. Their image source, alt, everything looks good. Then we got this theme picture shit. It has image alt. Then you click on something. It has it here. No opener, no refer. Okay. Well, same thing happened here with the A. And that's a valid link. Dark looks to be correct. Light looks to be correct. Then what is like disabling this? The picture element? Okay, I have saved the SVGs as two different files, foo light.svg and foo dark.svg. Show me how to embed them in GitHub README. Picture source media prefers color scheme dark, source set dark.svg. Image maybe the alt text? No. Source it files are in a subdirectory, yeah. What do my current files look like? Like if I go here and I look here, do they rewrite these? Probably. Yeah, they rewrite them. Well, let's test out a branch. Vim readme, and we'll do maybe another one here with a markdown thing. Bang, objectives, like that. Get status, get et al, get checkout B, test readme, get LGA, get CIM test, oops, get CIM test, and then get push origin test readme. I can go here just reload here. Go to test readme. Okay. This didn't work, but this did. No link. That's fine. And then if I switch over here to light mode, hey, it works. Yep. Okay, let's do that then. Vim readme. Delete this thing. Does not work that way, but does work this way. And I'll fix this one first. So it's gonna be instead of objectives, it'd be schedule 1 dark, schedule 1 light, and then we'll say schedule 1. And then here we'll do schedule 2. Schedule 2, schedule 2. Delete all that. Delete that, get status, get add all, get DC, get CI, test 2, get push, origin, test readme. Okay, that's very clear. Some of these could be made a little bit bigger, I feel. Maybe the spacing is a little bit large. But then if I go over here to settings and switch this to dark, everything dynamically adapts over to dark mode. Nice. It's pretty nice. We're gonna rebase onto master, and we're gonna squash everything, and we're going to, I think I'd say edit. Yeah, we just squash everything. We say enable light dark mode for objectives schedule images. Support light and dark mode for images. Get LGA. Okay. Here we could do a get push force origin test readme. And then we'll reload that. Yeah, okay, looks good. Dark mode. We'll go back to light here. Looks good. Dark. Alright, and then we do get LGA, get checkout master, get merge fast forward only with test readme, get LGA, get push. I wonder if Codeberg supports the light and dark mode too. Okay, get status, get LGA, get branch delete test readme, and get push origin test readme. Yeah, okay. Let's check out Codeberg. This is very much light mode. And if I switch over to light mode here, dark mode, Why is this not rendering? They strip out all the picture stuff. Can embed logic inside the SVG. Seems like a lot of work. Let's diff the two. So we go under images, delta between, let's just do like objectives, 2026 objectives light, and 2026 objectives dark. Okay, let's make this full screen. Wow, that's the only delta? That would be really easy to switch on then. It's just a different font face. Let's try doing that. So go back here. They're using this thing, media query. I think what I need to do is say Vim 2026 objectives light. Oh, but the whole fucking thing is a font face? What? No. Here we go. Here's the data. Let's find the end of the style, and then I'll put a return there. And then we'll do the same thing on, yeah, because this is just like continues on, and the entire thing's on one line. 2026 objectives dark.svg. There has to be other stuff that's like messed up here. Let's run delta. Oh, so the font face actually is identical. Okay, that's good to know. It's just these fill colors. Well, let's go back over to here and we say my SVGs use hard-coded fill attributes in the elements. How would you go about solving this? Remove adders, fill. we've gone down this path a little bit too far. Okay. Git status, git reset hard at. Okay. At least it works on GitHub. Kill that, kill that, kill that, kill that. Refresh here. Oops. Light mode. It works. Dark mode. It also works. Alright, that's enough navel gazing on that. Okay. Alright, we're just wasting time here. Continue reading. Alright, so we left off looking at this diagram, asking AI about how to measure clock cycles in between 2 points in time in a code, and there's some assembly instructions that allow you to do that. I do want to revisit that chat and ask it for CPU clock cycle measurement, is there an existing well-used library to take these measurements? Google benchmark, high resolution timing and statistics. Internal uses RDT SC on x86 when available. Falls back to clock get time if necessary. Automatically handles warm up, repetition, measuring tiny functions. Example. I need to check that out at some point. So Google Test and Google Benchmark are two libraries I feel like, they're C libraries that I feel like I need to spend more time with. I guess C++. Yeah, use auto colon. Is there a C version of this though? Requirements. It has to be a C++ project. Okay, I'm gonna put Google Test and Google Benchmark on my list of things to learn. let's just go ahead and grab them. Google test. This thing here, that's what I wanted. Yep, okay, good. So let's create another terminal here. And we'll jump over to learn log. We'll say docs. We're gonna add this thing. Google test and Google benchmark. And is there a IO website for this thing? Doesn't look like it. Okay, let's continue with the reading. What is the least squares fit? A set of data points x, y, x1, y1 to xn, yn. We often try to draw a line that best approximates the xy trend represented by these data. With a least squares fit, we look for a line in the form of y is equal to mx plus b that minimizes the following error measure. So the error given m and b, so b is your y-intercept, your m is your slope, it's equal to the sum between I and n. I is 1 or n. This is an initializer. Yeah, I've never seen this notation before. Yeah, I think he means like a shorthand where n is on the top. Probably easier for him to write that in LaTeX. So we're going from I to n, or sorry, from 1 to n, where we say evaluate mx plus b minus y. Usually just y is equal to mx plus b. So we subtract y from both sides to get the actual value. 0 is equal to that. And we square the value. And we sum all those up. An algorithm for computing m and b can be derived by finding the derivatives of e and b with respect to m and b and setting them to 0. E and b with respect to m and b and setting them to 0. That makes sense because then they're at the low point in the curve. I kind of want to do the exercise of doing this, like plotting out this thing in Desmos. And we say something like can I do a sigma in here? Is there a sigma? Doesn't seem like it. Functions. There we go, sigma. N is equal to 1. Can I say I here? I is equal to 1 n. Where this is going to be mx sub I. How do I do sub? Can I do sub here yet? Sub I plus b minus y sub I. Where's the sub here? Sub I. And then we square that. Says, sorry, I don't understand the way that that is used here. Okay, so we have to go over here and say E of M and B is equal to and we need some data here. Oh, this is wrong here. I need to do minus here. My bad, my bad, my bad. so we have our data set now. If we go down here and say L sub 0 sub, where'd you say L sub 0? We'll hide that. There's a single data point now. Label. Why is L sub 0 and L sub 1? Okay, so it's 1 indexed. Delete the label, thank you. Do I do like a sub x using like x like that? Dot x, maybe I have to wrap in parentheses. Okay, there we go. So you have to have the parentheses, you can't tack that onto that. Wait a minute, yeah you can. There we go, okay. So you just do dot x. So this would be m times L sub I dot x plus b minus dot y L sub I dot y so m and n are going to be parameters that we define here, and b, but the function that he gave m and b, n, what is n? We should not have an n here. Length of L. then I'm going to actually draw the line here. Where we just say, oops, y is equal to mx plus b. So m we want to be like that. B we want to be like something like that. You can see it's generally optimizing for a lower value. Okay. Something like that. Now we need the function of this, but it's a two-dimensional function. Desmos take a 2D derivative. First I want to plot it, but the thing is I can't plot both. Hey, sorry, Mr. Chat Mio. I'm trying to figure out the least squares fit, how that is actually computed. So I just have some like test data here, data points here, and then I created a MMB for my line here that fits the data and lowers this value. We're optimizing this value here. It's basically taking a square with all those values. But what I want to do is plot this, but it has two variables, m and b. I guess I could sub out m and b and just say, hey, let's do f of mb is equal to that. Well, does that make it plottable? No. What if we say we just want y? F of m. So we could have two different functions here. Can I duplicate this? Just copy it. Place it down here. F of b. But f of m and b, we can't plot that because it's two-dimensional. Well, we know that the lowest value of b 0.7 0.7, yeah. And that's given to us by this function here. And then the lowest value of m is 1.62. So if these are just like all crazy values here, I would say, okay, 3.5 would be the best value for m. And then you go over here and say negative 3.1 would be better value. And then you just repeat this 3.25. Almost gets to 0 there. Well, let's go ahead and... Can I delete this? No, it deletes the entire thing because we need B to be a slider even though M is parameterized. Yeah. Okay, well down here we could take the derivative of a function. So you can see here f prime of a, x minus a, what the fuck? So f of x is sine x. F prime of a times x minus a. Or you can just do f prime of x. Okay, this is plotting it. This is m is the slope of the tangent, x plus b. Okay, that makes sense. So you just say f prime of x. Okay, let's do it. F, and we want to call this like b, g. We'll call this g of b. And we want to say f prime of m. Why is that a single value? If f of m, oh, because m is known. So you want this to be 0. Bring this to 0. And then f or g prime of b, 0.6. Can I lower this even further? I would like to see these derivatives. Can I say y is equal to that? Y is equal to that. So we just slide these things to lower these values down to almost 0. That's pretty close there. Eight 8.1, 8.7, 1.8, 1.78, 9. Ooh, so close. 5. No. 3. That's pretty close. I think we should use separate variables here. So this is f of m, and it has a b in it. This will be g of c, and it has an n in it. This will be c here. So that means that m will have its b, so we can eliminate the m there, and we add an n. And x plus b. Now this becomes plottable, right? Let's go back here. F of m, m and b. We don't want, we want b to be concrete here. We want c to be concrete here, and to be concrete there, c to be parameterized. B concrete, n concrete, C, C, okay. So now they're independent. We want to get this to 0. Get that to 0. And then this guy here, can I change these colors? But we have y of f of m, f prime of m. Y is equal to f prime of m. Okay. Y is equal to g prime of b. But we want this to be c. G prime of c. Okay, basically wherever these two things intersect, 0. Wait a minute. Because b is changing. What does that represent? I don't know. Down here, we want to say y is equal to m or n mx plus b, but our m is actually an n. There we go. Yeah, it's like it's a two-dimensional derivative. It's hard to plot. I think I need to get better at 2D derivatives. But I'm going to do the little savey save here. Can I not export this? I definitely have an account here. Give me 1 second. I need to log in here. I definitely have an account. But I don't want to save it on my account. I want to save it to Git repo. Let's jump over to Desmos. Okay. There we go, Desmos. This will be least squares fit. Quit that, eject that, do that. So if I add another data point here, I could conceivably throw this whole thing off, which is like, we'll do like 20, or we'll do 4, -3. Sorry, 4, -3, like that. But just adding that there just threw everything off. You see these things went crazy. So I would have to adapt it. Should be bringing this guy down here. Oops. Looks like that is the lowest fit I can get. Lowest there, lowest there. Yeah, that's the fit. But we'll undo that because we don't want that extra data point messing things up. Oh, you can do like a 3D graph just by adding Z. Maybe I try changing this into a 3D. Can I say convert to 3D? Gear here. Done. I'm not going to spend any more time on this. That'll be a fun thing to come back to when I study more calculus. All right, let's continue onwards. For large values of n, say greater than 200, the runtimes will be dominated by linear factors. We refer to coefficients in these terms as the effective number of cycles per element. We prefer measuring the number of cycles per element rather than the number of cycles per iteration, because techniques such as loop unrolling allow us to use fewer iterations to complete the computation. But our ultimate concern is how fast the procedure will run for a given vector length. We focus our efforts on minimizing cycles per element for our computations. By this measure, psum2 with a CPE of 6 is superior to psum1 with a CPE of 9. Practice problems. Later in this chapter, we will start with a single function and generate many different variants that preserve the function's behavior, but with different performance characteristics. For 3 of these variants, we found that the runtimes and clock cycles can be approximated by the following functions. For what values of n would each version of the fastest? For what values of n would each version be the fastest of the 3? Remember that n is always be an integer. Okay, so it's not hard to solve here. 5.2, we'll say version 1, 2 and 3. So if n is equal to 0, then the terms on the right go to 0. So we say n is equal to 0. We can just plot these. This would be a good thing for Desmos. Desmos, we'll just say y is equal to 136 plus 4n. These are all linear situations here. Y, sorry, 136x, 4x. Y is equal to 157 plus 1.25x. And then we'll give the other one too. 60, y is equal to 60 plus 35x. And we need to zoom out a little bit here. So you want the lowest value. 2.45. Yeah. n is less than 2.45 161. And then after that, red takes over, which is 136, which is version 2. So it'll be up to here, which is 763,636. 763,636. We'll say n is less than that, but it's greater than this. And then this will just be, oops. After that. Okay, well, oops, do this. All right, 5, 4, 5, 2 here. The relationship between CPE and the absolute performance. It can be solved using elementary algebra. We find that for n is less than 2, version 1 is the fastest. Version 2 is fastest from 3 to 7. Version 3 is fastest for n is greater than or equal to 8. Not quite true. Yeah. Not quite true, because just look here. Version 1 is fast as n is less than or equal to 2. Well, that's true, but it's also here. So if we look at from 3 to 7, yeah. Okay, that's right, from 3 to 7. Be up to here. And then you skip from 7 to 8, and then you say, hey, and greater than or equal to 8. But these are a little bit more precise numbers. Okay, so they're not wrong there, but they just kind of skipped over the areas of conflict. Leave. Okay, program example. To demonstrate how an abstract program can be systematically transformed into more efficient code, we will use a running example based on the vector data structure shown in figure 5.3. A vector is represented with 2 blocks of memory, the header and the data array. The header is a structure declared as follows. Length and data, yeah. Vector abstract data type. A vector is an abstract, or is represented by a header information plus an array of designated length. So it's a pretty common vector header pattern. The declaration uses data T to designate the data type of the underlying elements. In our evaluation, we measure the performance of our code for integer, cint and cint and long, and floating point, float and double data. We do this by compiling and running the program separately for different type declarations, such as the following for data type long. We allocate the data array block to store the vector elements as an array of length objects type data T. Figure 5.4 shows some basic procedures for generating vectors, accessing vector elements, and determining the length of vectors. An important feature to note is that getVecElement, the vector access routine, performs bound checking for every vector reference. This code is similar to the array representations used in many other languages, including Java. Bound checks reduces the chances of programming error, but it can also slow down program execution. As an optimization example, consider the code shown in figure 5.5. which is 2 pages ahead, which combines all of the elements of the vector into single value according to some operation by using different definitions of compile time constants, ident, and op. The code can be recompiled to perform different operations on the data, in particular using declarations ident 0, op is plus. It sums the elements of the vector. Using declaration ident 1 and op star, it computes the product of the vector elements. Our presentation, we will proceed through a series of transformations of the code, writing different versions of the combining functions to gauge progress. We measure the CPE performance of the functions on the machine with an Intel Core i7 Haswell processor, which we refer to as our reference machine. Some characteristics of this processor were given in section 3.1. These measurements characterize performance in terms of how the programs run on just one particular machine. And so there's no guarantee of comparable performance on other combinations of machines in compiler. However, we have compared the results with those for a number of different compiler processor combinations, and we have found them generally consistent with those presented here. As we proceed through this set of transformations, we will find that many lead to only minimal performance gains, while others have more dramatic effects. Determining which combinations of transformations to apply is indeed part of the black art of writing fast code. Some combinations that do not provide measurable benefits are indeed ineffective. While others are important as ways to enable further optimizations by the compiler. In our experience, the best approach involves a combination of experimentation and analysis, repeatedly attempting different approaches, performing measurements, and examining the assembly code representations to identify underlying performance bottlenecks. All right, let's look at the code. So we got a vec pointer, new vec, give it capacity or length. This thing allocates the header structure. So before, we already defined the header as a vec rect, or a pointer to a vec pointer. Okay. So we have malloc size of vec rect, and we cast that to a vec pointer. And then we initialize a local data pointer of null. And we say, hey, if the result was null, then we're just going to return null. We couldn't allocate. And then we set our length to the length provided. And then we allocate the array itself. So if length is greater than 0, then we need to do some allocation. So we say calloc, we give it the length and the size of data t, and we say that's a data t pointer, we assign it to data. If data was null, then we free the result that we got from the initial malloc, and then we return null because we can't do the calloc. Assuming the calloc and the malloc both succeed, then we assign the data pointer into result data, and we return result. We hold off on doing that to make sure that everything has succeeded before we mutate the data field. It's like, do all the work, make sure there's no errors. If there's errors, abort, signal the errors. If there's no errors, mutate the structure, return. Cool, cool, cool. I guess it wouldn't be super important in this situation because they didn't pass in the vec pointer. So, I don't know. They didn't really need to have a separate data here. They could have just assigned into the result. Yeah. Okay. And then they have get vec element, where they take retrieve vector element and store at destination. So we give it the vector, we give it the index, and the place that we want to write the data to. And they say, hey, if index is less than 0 or is greater than or equal to the length, then we got an out of bounds issue. We're just going to return 0. We should return like -1 as like an error signal. VData index then gets assigned at the destination, and we return 1. Okay, return length of vector. Vec length just returns a length field. It's pretty straightforward. And then finally, implementations with maximum use of data abstraction. So we have combine, vector, so implementation with maximum use of data abstraction. So we combine the vector with the data T destination. Combine one, I don't know what this combine one, initial implementation of combining operation. Oh, is that to just like do a sum? Okay, that's what we were talking about before. Okay, using different declarations of identify element ident and combination operation op, we can measure the routine of different operations. So op is going to be an operator, and then ident would be the initial value at destination. I don't know why we need ident there, because destination is passed in and then mutated. What does ident mean? I don't know, even know. Okay. As a starting point, the following table shows CPE measurements for combine one running on our reference machine with different combinations of operations, addition or multiplication, and data types. Data type long integer, double precision floating point. Our experiments with many different programs show that operations of 32, 64-bit integers have identical performance, with the exception of code involving division operation. Similarly, we found identical performance for programs operating on single or double precision floating point data. In our tables, we will therefore show only separate results for integer data and for floating point data. Where am I at on my calendar here? Okay, I got 45 minutes remaining before I break for lunch. I really want to get another burrito today. Those burritos have been really good. All right. So we have this combine. Actually, I'm going to jump over here. Go to, README. Go up here. We are on 5.4, eliminating loop efficiencies. That's how much progress we've made so far in chapter 5. Not a lot. But yeah, making some progress. So we have combine one, which we have abstract unoptimized, abstract 01. So we can get addition and multiplication down basically to 10 cycles per element from 20 roughly for all operations. We can see that in our measurements, we can see that our measurements are somewhat imprecise. The more likely CPE number for integer sum is 23 rather than 22.68, while the number for integer product is likely 20 instead of 20.02. Rather than fudging our numbers to make them look good, we present the measurements we actually obtained. There are many factors that complicate the task of reliably measuring the precise number of clock cycles required by some code sequence. It helps when examining these numbers to mentally round the results up or down by a few hundredths of a clock cycle. The unoptimized code provides a direct translation of the C code into machine code, often with oblivious inefficiencies. By simply giving the command line option 01, we enable a basic set of optimizations. As can be seen, it significantly improves the program performance more than a factor of 2 with no effort on behalf of the programmer. In general, it's good to get into the habit of enabling some level of optimization. Similar performance results were obtained with optimization level OG. For the remainder of our measurements, we will use optimization levels 01 and 02 when generating and measuring our programs. Eliminating loop inefficiencies. Observe that procedure combine 1, as shown in figure 5.5, calls function, eject this thing, combines function observe the procedure combine 1 is, as shown in figure 5.5, calls function vec length as a test condition for in the for loop. Yeah, vec length. And that just returns the length. That should be inlined. Get vec element. I guess there is function call overhead there, but it should be inlined. As a test condition for loop, recall that our discussion of how to translate code containing loops into machine level programs, that the test condition must be evaluated on every iteration of the loop. On the other hand, the length of the vector does not change as the loop proceeds. We could therefore compute the vector length only once and use this value in our test condition. Figure 5.6 shows a modified version of combine 2. It calls vec length at the beginning and assigns the result to local variable length. This transformation has no noticeable effect on the overall performance for some data types and operations, and minimal or even none for others. In any case, this transformation is required to eliminate inefficiencies that would become bottlenecks as we attempt further optimizations. So just moving vec length reduce significantly integer summation and some of the other ones. Okay. This optimization is an instance of a general class of optimization known as code motion. Code motion. They involve identifying a computation that is performed multiple times, e.g. within a loop, but such that the result of the computation will not change, and can therefore move the computation to an earlier section of the code that does not get evaluated as often. In this case, we move the call to vec length from within the loop to just before the loop. Optimizing compilers let me look at the code here. Improving efficiency of the loop test by moving the call of vec length out of the loop test. We eliminate the need to execute every iteration. Yeah, I mean, it's a very fast function that could be inlined. It could just be a memory reference, but again, it's a memory reference. Every single iteration that you don't need to do, you can assign it into a register and use it as a register reference. Okay. Optimizing compilers attempt to perform code motion. Unfortunately, as discussed previously, they are typically very cautious about making transformations that change where or how many times a procedure is called. They cannot reliably detect whether or not a function will have side effects, and so they assume that it might. For example, if vec length had some side effect, then combine 1 and combine 2 could have different behaviors. To improve the code, the programmer must often help the compiler by explicitly performing code motion. As an extreme example of loop inefficiency seen in combine 1, consider the procedure lower 1, shown in figure 5.7. This procedure is styled after routines submitted by several students as part of their network programming project. Its purpose is to convert all of the uppercase letters in a string to lowercase. The procedure steps through the string, converting each uppercase character to lowercase, and the case conversion involves shifting characters in the range A to Z to the ranges A to Z. Library function strlen is called as part of the loop test of lower 1. Although strlen is typically implemented with special x86 string processing instructions, its overall executing is similar to simple version that is shown in the figure 5.7. Since strings in C are null terminated character sequences, strlen can only determine the length of the string by stepping through the sequence until it hits a null character. For a string of length n, strlen takes time proportional to n. Since strlen is called in each of the n iterations of lower 1, the overall runtime of lower 1 is quadratic in the string length proportional to n squared. So if we look here, we got lower 1, lower 2, and strlen. So lower 1 converts string to lowercase. It calls strlen in the condition. Lower 2 computes the length one time. and then just reuses that computation from a register. This analysis is confirmed by actual measurements of the function for different length strings as shown in figure 5.8, and using the library version of Stirlen, the graph of the runtime for LoRa1 rises steeply as the string length increases. 5.8b shows the runtimes of several different lengths not the same as shown in the graph, each of which is a power of 2. Observe that the lower one, each doubling of the string length causes a quadrupling of the runtime. This is a clear indicator of a quadratic runtime. For the string of length 1 million, lower one requires over 17 minutes of CPU time. Compared to performance of lowercase conversion routines, the original code LoRa1 has a quadratic runtime due to an inefficient loop structure. The modified code LoRa2 has linear runtime. Okay, so that's a asymptotic optimization. Algorithmic asymptotic optimization. Function LoRa2 shown in a figure. Okay, we're almost on 5.5 here. We just have one practice problem. We could probably do that before the hour. Function LoRa2 shown in figure 5.7 is identical to that of LoRa1, except that we have moved the calls to. Did I already read this? Did I? The performance improves dramatically for a string of length 1 million. The function requires just 2 milliseconds, over 500,000 times faster than LoRa1. Each doubling of the string length causes a doubling of the runtime, a clear indicator of linear runtime. For longer strings, the runtime improvement will be even greater. In an ideal world, a compiler would recognize that each call to Stirlen in the loop test will return the same result, and thus the call could be moved out of the loop. This requires very sophisticated analysis since Stirlen checks the elements of the string, and these values are changing as LoRa1 proceeds. The compiler would need to detect that even though the characters within the string are changing, none are being set from non-zero to zero or vice versa. Such an analysis is well beyond the ability of even the most sophisticated compilers, even if they employ inlining, and so programmers must do such transformations themselves. This example illustrates a common problem in writing programs in which a seemingly trivial piece of code has a hidden asymptotic inefficiency. One would not expect a lowercase conversion routine to be a limiting factor in a program's performance. Typically, programs are tested and analyzed on small data sets for which the performance of LoRa1 is adequate. When the program is ultimately deployed, however, it is entirely possible that the procedure could be applied to strings over 1 million characters. All of a sudden, this benign piece of code has become a major performance bottleneck. By contrast, the performance of LoRa2 will be adequate for strings of arbitrary length. Stories about a major programming project in which problems of this sort stories abound of major programming projects in which problems of this sort occur. Part of the job of a competent programmer is to avoid ever introducing such asymptotic inefficiency. I'm going to highlight that because I agree with it, and most people don't ever consider their shit when they're slopping out garbage, especially with AI. Okay, practice problem 5.3. Let's go ahead and open problems. 5.3. So consider the following instructions. Consider the following functions: min, max, increment, and square. So min takes the minimum, max is the inverse, except for the equals. No, that would be the inverse, yeah. And then increment takes a pointer to something to add v to. And then square takes a long and returns its square. The following 3 code fragments call these functions. Oh, we get to do a table. Yay. It's been a while since we had to do a table. Markdown. Table generator. Okay, file, new table. And it's going to be 1, 2, 3, 4, 5 by 1, 2, 3, 4. 5 columns by 4 rows. Great. Up here we have code. Code. Min, max, incur, square. Incur, square. And they have A, B, C. Generates, copy. Okay. So the following 3 code fragments call these functions. So we have min, max, incur, square. Max, min, incur, square. Min, max, low, high, incur, square. So basically we're doing the square in the body, or incur is on the right, and min max is part of the initializing condition. Assuming x equals 10 and y equals 100, fill in the following table indicating the number of times each of the 4 functions is called in code fragments A through C. So we'll just do A first. So min will be called once, because it's initialized. Max will be called n times. So I'm not sure what n is. Incur will be called n times as well. No, it's called, let's see. If we're doing x equals 100, so min will be 10, less than max will be 100, so max will get called 90 times roughly. Increment will be 90. This will be something like 91. This will be something like 90. And this will be something like 90. But let's get exact numbers here. So say it's a lower number here. Say we're going from 3 to 5. Then we would have min getting called once. Min is always called once. Max would get called once at the initial entry into the function. So max, and then square, incur, max, square, incur. So that would be for 3. 3 is less than 5, so this would be incur to 4. So this incur took us to 4. This incur will take us to 5. 5 is less than 5 is not true. So then we'll have a max call to do that comparison. So here, with our range of 3 and 4, we had max going to 3. So 3, 4 range, yeah. 2 iterations. Max got called 3. Square got called 2. Increment got called 2. Okay. So it's going to be 3, 2, 2. So it's like I was saying, like max gets called one extra time. How many iterations here? It's less than 100. So it's 10 to 100. Well, 5 minus 3, so it'd be 100. It'd be 90. I think this is correct. But just check the back of the book. 191, 90, 90. A. What problem is this again? 5, 3. Why are we on 5, 8? Oh no, here it is. 5, 8. 91, 90, 90. Yep. Okay. Let's do the next one, which is B. So in this case, max is going to be our 1. Just delete all this stuff here. Min. Well, we can do a little scratch here. So if max was say like 5, so now I is equal to 5. Max would be equal to 4. 4. And then I is greater than or equal to 3. So this would be our max, which sets I is equal to 4. And then we'll have a min check here. I is greater than or equal to the min call, which is 3. And then anchor, then we do a square, we do anchor, -1, square I, anchor, now I is equal to 3. Now we're on our next iteration, which we don't have a max, but we do say min I is less than or equal to 3, yes, square, anchor, I is equal to 2. And then on here we'll have our last min I is greater than or equal to 3, which is not when we exit. So we had 2 iterations. So it's going to be similar here. Where it's going to be started at 100 going down to 9. So min will be 91, I believe. Anchor would be 1, 2, so that'd be 90. And square would be 90 as well. Let's see if that's correct. B 91, 1, 90, 90. Yep. And then C, if we work through that, min and max will be called once. Min, max. Anchor will be 90. Square will be 90. Yep. The little blurb of text they had here was that this is a simple exercise, but it is important to recognize that 4 statements of a for loop initial test, update, and body get executed different numbers of times. Reducing procedure calls. As you have seen, procedure calls can incur overhead and also block most forms of program optimization. Do I want to continue with 5.5? I think I have until like noon, yeah. Okay. Well, let's go ahead and save this. Delete these new lines here. Save that. Jump over to the README. And we'll mark 5.4 as done. These aren't too hard sections. I'm sure it gets harder. As you've seen, procedure calls can occur. Okay. As we've seen, procedure calls can occur overhead and also block most forms of program optimization. We can see the code for combine 2 figure 5.6. Go back in time here. Combine 2, which is where we just pulled out the vec length. The get vec element is called every loop iteration to retrieve the next vector element. This function checks the vector index I against loop bounds with every vector reference. A clear source of inefficiency. Bounds checking might be a useful feature when dealing with arbitrary array access, but a simple analysis of the code for combine 2 shows that all references will be valid. Yeah. Because we compute it based on its length. So get vec start. And this eliminating function calls within a loop. Resulting code does not show a performance gain, but it enables additional optimizations. So we just pull out the get vec start as data. And why did we do that? Because we're not using data anywhere else. Wait a minute, what are they doing here? At the start, it needs to do a plus plus on data. Oh no, it does that by I, data sub I. Okay. Doesn't mutate data, but it uses the offset of data. Okay. I figured that would be an improvement because getVec element does the bounds checking. You're not doing bounds checking anymore. Suppose instead we add a function getVecStart to our abstract data type. This function returns the start address of the data array as shown in figure 5.9, where you could then write the procedure shown in combine 3 in this figure, having no function call as an inner loop rather than making a function call to retrieve each vector element. It accesses the array directly. A purist might say that this transformation seriously impairs the program modularity. In principle, the user of the vector to abstract data type should not even need to know that the vector contents are stored in an array rather than as some other data structure such as a linked list. A more pragmatic programmer would argue that this transformation is a necessary step towards achieving high performance results. So we move vec length was combined 2, combined 3. We didn't get much improvement. We did eliminate the bounds checking. Surprisingly, there's no apparent performance improvement. Indeed, the performance of integer sum has gotten slightly worse. Did it? Yeah, it did. Interesting. Evidently, other operations in the inner loop are forming a bottleneck that limits the performance more than the call to getVec element. We will return to this function later and see why the repeated bounds checkings by combine 2 does not incur a performance penalty. For now, we can view this transformation as one of a series of steps that will ultimately lead to greater improved performance. Eliminating unneeded memory references. Wait a minute, that's a whole section there? It's like 2 pages? Okay. Wait a minute. Eliminating unneeded memory. Okay. Okay. The code for combine 3 accumulates the value being computed by the combining operation at the location designated by the pointer destination. These are such small sections, making a lot of progress here. The code for combine 3 accumulates the value being computed by the combining the operation at the location designated by the pointer test. But that means that we're going out to main memory, or at least the cache, every single time we want to do an assignment instead of doing the assignment into a register. This attribute can be seen by examining the assembly code generated from the inner loop of the compiled code. We show here the x86-64 code generated for the data type double and with multiplication as the combining operation. Yeah, it's doing XMM move of RBX address dereference into XM0 and then move back into that location. We see this loop code that the address corresponding to pointer destination is held in register RBX. It has also transformed the code to maintain a pointer to the ith data element in register RDX, shown in the annotation as data +1. This pointer is incremented by 8 on every iteration. The loop termination is decided by comparing this pointer to one stored in register REX. You can see that the accumulated value is read from and written to memory on each iteration. This reading and writing is wasteful since the value read from destination at the beginning of each iteration should simply be the value written at the end of the previous iteration. We can eliminate this needless reading and writing to memory by rewriting the code in a style of combine 4. In figure 510, we introduce a temporary variable accumulator that is used in the loop to accumulate the computed value. The result is stored at destination only after the loop has been completed. As assembly code that follows shows, the compiler can now use register XMM0 to hold the accumulated value. Comparing to the loop in combine 3, we have reduced memory operations per iteration from 2 reads and 1 write to just a single read. So we've got this inner loop. We do our multiply of the data in RDX by XMM0 and stored in XMM0. And then we increment that data pointer by 1. And we compare REX to RDX to see if we're in bounds. If not, we jump. We see significant improvement in the program performance as showed in the following table. Holding the accumulated value in local variable ACC, short for accumulator, eliminates the need to retrieve it from memory and write it back to updated value in every loop iteration. Combine 3. 549, direct data access. Combine 4 is accumulated and temporary. So that got us a lot of improvement, not doing all those memory accesses. All of our times improved by factors ranging from 2.2x to 5.7x, with the integer addition case dropping just 1.27 clock cycles per element. Again, one might think that compilers should be able to automatically transform the combine 3 code shown in figure 5.9 to accumulate the value in a register, as it does with the code for combine 4 shown in figure 5.10. In fact, however, the two functions can have different behaviors due to memory aliasing. Consider, for example, the case of integer data with multiplication as the operation and 1 as the identity element. So let v is equal to 235 be the vector of 3 elements, and consider the following 2 function calls. Okay, so we go to the start plus 2 gives us the end value, and we're going to combine 3. Oh, it gets mutated, and then combine 4. Okay, that is, we create an alias between the last element of the vector and the destination, so storing the result. The 2 functions would then execute as follows. So the final result is 236. Okay, that's the destination. So it's writing the value of the destination. It's 36. Yeah, it's semantically different. As shown previously, combine 3 accumulates its result in the destination, which is, in this case, is the final vector element. This value therefore is set first to 1, then to 2 times 1, and then to 3 times 2. In the last iteration, the value is then multiplied by itself to yield the final value of 36. For the case of combine 4, the vector remains unchanged until the end, when the final element is set to the computed result of 1, 2, 3, 4, 1, 2, 3, 5, which equals 30. Of course, our example showing the distinction between combine 3 and combine 4 is highly contrived. One could argue that the behavior of combine 4 more closely matches the intention of the function description. Unfortunately, a compiler cannot make a judgment about the conditions under which a function might be used and what the programmer's intentions might be. Instead, when giving combine 3 to compile, the conservative approach is to keep reading and writing to memory, even though it's less efficient. Practice problems. Oops. 5.4. Oh, yeah, 5.4. Yeah. Okay. When using GCC to compile combine 3, with command line option 02, we get code with substantially better CPE performance than with 01. Okay. We achieve performance comparable to that of combine 4, except for the case of integer sum. Integer sum's a little bit better, but not identical. But even it improves significantly. On examining the assembly code generated by the compiler, we find an interesting variant of the inner loop. We can compare this to the version created with optimization level 1. See that besides some reordering of instructions, the only difference is that the more optimized version does not contain the vmove SD implementing the read from the location designated by destination. Okay, so we've got an A, a B, and a C. So the first one is, how does the role of x of m0 differ in the two loops? So in the first one, x of m0, it looks like it's doing an initial read and then a store. So x of m0 is used as the accumulator. And it's also storing. So we'll say xm0 is used as an accum that is read and written each iteration, versus here we say xmm0 is explicitly set to the value in destination on the second version. Yeah. Will the more optimized version faithfully implement the C code of combine 3, including when the memory aliasing between destination and vector data? No, because we're not doing a read. We're doing a read from RDX, but not a read from destination. No, we are not doing a... I guess we're doing the write. I guess maybe... We do a read for the multiplication. We're not doing a read for the accumulation. We are assigning into every element, so you will read it on the last iteration. We'll say yes. Yes, because it is written out to memory at the end of every iteration. And then C, either explain why this optimization preserves desired behavior, or give an example where it would produce different results than a less optimized version. Because it gets written out. Because the register state gets written out. Look at the original code of combine 3. Where's combine 3 at? Because the register state gets written out to memory, the 2 at the end of every iteration, the 2 stay in sync, and the appropriate value is read later by indexing against data. Okay, let's see what they say. 5.4. This assembly code demonstrates a clever optimization opportunity detected by GCC. It's worth studying this code carefully to better understand the subtleties of code optimization. In the less optimized code, register XMM0 is simply used as a temporary value, both set and used on each loop iteration. In the more optimized code, it is used more in a manner of a variable accumulator in combine 4, accumulating the product of the vector elements. The difference with combine 4, however, is that the location destination is updated on each iteration by the second move as the instruction. You can see that the optimized version operates much like the following C code. Yeah. So it prevents one read from destination. We're just doing writes out to destination, which I guess because it's in the cache, it's pretty fast. The 2 versions of combine 3 will have identical functionality even when memory aliasing. This transformation can be made without changing the program behavior because, with the exception of the first iteration, the value read from destination at the beginning of each iteration will be the same value written to this register at the end of the previous iteration. Therefore, the combining instruction can simply use the value already in XMM0 at the beginning of the loop. Okay. With this final transformation, we reach a point where we require just 1.25 to 5 clock cycles for each element to be computed. This is a considerable improvement over the original 9 to 11 cycles when we first enabled optimization. We would now like to see just what factors are constraining the performance of our code and how we can improve things even further. Okay, it's almost noon here, so I'm going to update my README. Go up here. We're now on 5.7. Oops. Let's go ahead and just write and quit everything. Get status, get at all, get DC. So we got our problems. Looks good. Get status. We'll say progress and get LGA. Progress on chapter 05. Get push all. Okay. Now I'm gonna go get lunch, and I will be back. Do lunch and cardio, 30-minute cardio, and I'll be back in this afternoon at 1:30 for an afternoon stream where we will do more optimization stuff. This chapter is actually going pretty fast. We're at 5:52 now. We started on 5:31, so that's 20 pages we've read already. If we can get another 20 pages in this afternoon, 30 pages, if we get another 30 pages in this afternoon, I would be really happy with that amount of progress. That's 50 pages of super technical stuff with problems. So yeah, cool. All right, I'm gonna go get lunch. I'll be back later.